We're now going to do some more examples of the substitution method here. So this first one, you can see that you have this function, 1 minus x squared, inside or underneath a radical. And if that is the inside function, then its derivative would just be negative 2x. And we have an x on the outside. We just don't have the negative 2. So the derivative of this inside function is hanging around on the outside up to a constant multiple. It's just different by a constant multiple. So what I'm going to do is I'm going to let u equal 1 minus x squared. And so then du, and then what I'm going to do is I'm going to take the derivative of this, which would just be negative 2x, and then I'm just going to put the dx there, just to save a step. Okay? And so I'm taking du dx is equal to negative 2x, and then I'm bringing the dx to the other side. And now this negative 1/2 can go down here. So what I'm left with is just x dx. So what I could do is I could rewrite this like this if I wanted to, if it helps. You don't have to do this. But what this shows here is that what you want here is a dx to substitute in, and the dx is negative 1/2 du, and you just have a constant there. So in for here, I put u, in for all this, I put negative 1/2 du, and then what I get here is the square root of u, and then I have like a minus 1/2 du, and so I can pull out the negative 1/2, and then I can rewrite this as u to the 1/2 du, and so now this would just be negative, this would be u to the 3/2 over 3/2 plus c, and then I can invert negative 2/3, invert the fraction on bottom, and then here I'm just going to plug in 1 minus x squared in for u, and then I got a 3/2 here, and then plus c. And so that would be the antiderivative of that. Okay? Okay, so now what about this one here? This one might be a little trickier to see, but it wouldn't be trickier to see if I wrote sine squared x as this, sine of x, that quantity squared, which is exactly what it means. Sine squared x actually means sine of x times sine of x. Okay? And then what we can see here is we have a sine of x hanging out on the inside of an x squared function. Okay? And then the derivative of sine of x is a cosine x, and that is hanging out here. So I'm just going to let my u equal sine of x, and then my du would be cosine x times dx. Again, I skipped that step. And there's my substitution, cosine x dx here. I put in du, and then in for sine x here, I put in u. So this thing would just be u squared du. Simplifies down quite nicely. Then I get u cubed over 3 plus c. And now I can put in the sine of x in for u. And so I might move the 1/3 off, and this would be like sine of x cubed plus c. And then this is normally written sine cubed x plus c. And so that would be the antiderivative. Let's see here. Okay, so I got a lot going on up here. I got e to the square root of x, and all that is divided by the square root of x. Okay, like this it might be a little bit hard to see, but if I wrote it like this, e to the square root of x, and then wrote 1 over the square root of x dx, then it's a little bit easier to see, because I know that if I let u be the square root of x, that's the inside function, it's inside a e to the x, then I know the derivative du, I'm bringing down, this is like x to the 1/2, right? And so I'm bringing down a 1/2, and then I got x to the negative 1/2, and then I'd have a dx here. But what I notice here is I'm going to bring this 1/2 to the other side, so I get 2 du, and then this x to the negative 1/2 is 1 over the square root of x dx. So bringing that 2 to the other side, then what I have here is what I have over here. They equal. And so I can do the substitution. I'm going to put in 2 du in for all of this, and then in for that I put u. U is equal to the square root of x. So this whole thing is equal to e to the u times 2 du, and then I could bring that 2 out, and I just have eu du, and of course that would just be eu plus c, because the derivative, or the antiderivative of e to the u is just e to the u. And then I can put the square root of x in for u, so I get 2e to the square root of x plus c. And that would be the antiderivative of that. For each one of these, go ahead and take the derivative of this using the chain rule and see if you get that. You should get that. So what about this one? This doesn't look like there's any inside or outside function. This is just the tangent of x. So what we're going to do is I'm going to use substitution to actually find the antiderivative of tangent of x. And the way that I do this is, let me rewrite rewrite tangent of x as the sine of x over the cosine of x dx. Okay, so I'm just going to write it like this, and then the derivative of cosine. So if I let my u equal the cosine of x, if I let u be the cosine of x, then du is going to be opposite sine x dx. And if I rewrote this, it would become maybe a little more obvious here that this is like 1 over the cosine of x, and then I get sine of x dx. So I got that negative sign, so let me bring it over here. Negative du is equal to sine x dx, and there you go. This is equal to that, so in for all this, I can put negative du, okay, and then in for this cosine x, I can put in u. So when I put in negative du, I'm just going to put my negative out front, and then I get the integral of 1 over u du. Okay, because I'm putting u in for here, in for all this, I'm putting negative du, and I just put my negative sign out front like that. And so this is just the integral of 1 over u du. Remember, that is not the power function. That is the integral of 1 over x is natural log of x, or natural log of the absolute value of x. So this would be natural log of the absolute value of u plus c. And so in for u, then I can put the cosine of x. So this is minus natural log of the cosine of x plus c. And that would be, so there, that is actually the antiderivative of tangent of x. Kind of a weird antiderivative, but that is the antiderivative. But what you would normally see in a list of antiderivatives, what's normally given is that the antiderivative to the tangent of x d of x is equal to the natural log of the secant of x plus c. And so how does that work here? Because this is what we got when I used the substitution method. This is what they normally give. So as it turns out, these are equal to one another, and let's see if I can show you that. Natural log of the secant of x is really equal to the natural log of 1 over the cosine of x, like this. And if you remember, I don't know if you remember, but you can split up the absolute value over top and bottom. So this would be equal to like the absolute value of 1, which is 1 over the absolute value of cosine x. You could write it like that. And then what I can do here is there's a property of logs. If you remember, if you have a log of a over b, this is equal to the log of a minus the log of b. And that's what I have here, so I can rewrite this as the natural log of 1 minus the natural log of the absolute value of the cosine of x. And natural log of 1 is just equal to 0, so this is equal to the natural log, the opposite of the natural log of the cosine of x. And so indeed these two are equal. Okay, what you would normally see, and I think they use this just because you don't have the negative sign to worry about. And oftentimes tangent and secant are related to one another, like in the Pythagorean identity. So that's kind of interesting there. So using the substitution, we actually found the antiderivative to the tangent of x. So those are just some other examples. I did those fast. This takes a lot of practice. I've been doing it for a long time, so you got to be able to look, find a composition, an inside function inside some outside function, where you see its derivative hanging around on the outside, and then let u be that inside function, and then you can go from there. But sometimes it takes a little bit of, sometimes you even have to manipulate or write things in a different way so that you can see it. It takes time. Of course, I made that look pretty easy. But those are some other examples of the substitution method in action. So, in the next video, well, I'll just wait to the next video to tell you.